Hello everyone, I am Amir Shahosani from Hyperlyceum, and in this session I will provide an introduction to simulation and make an attempt to address a number of important questions such as what is simulation, why is it necessary, what are its main elements, and what are its limits. Before delving too deep into the concepts and definitions of simulation, it is important to understand why is simulation essential in today's world and why all the leading companies are using simulation as a principal tool in the development of their products and services. The first reason is rather straightforward. By using simulation, you create a safe and virtual environment that can be used to emulate the behavior of different systems and phenomena, and therefore you avoid environmental hazards that would have been otherwise faced, that is, if you try to make the real-world products. As a direct result of having a virtual environment, the costs of testing and verifying the quality of the products, models, and systems are dropped drastically, because to test a system using simulation, you would only need to have a computer and an adequate model. Nevertheless, the same progress would cost much more if the system or product is to be made physically and then diagnosed. Bear in mind that simulation does not eliminate the necessity of prototyping, but rather enhances the quality of the prototypes. The third reason for the essentiality of simulation is that it can provide insight on the unexplored behavior of the dynamics. When running simulations, it is possible to examine the behavior of the system under different conditions and via different parameters. In fact, and contrary to prototyping, the characteristics of the systems and models can be easily changed to evaluate their effects. An additional benefit of using simulation is that it can provide visual aids. By running a simulation and obtaining the result, it is possible to use graphical tools at our disposal to observe the behavior and check if the system is behaving as intended. Visualization also simplifies the diagnosis procedures. Last but not least, simulation helps us save time. It is possible to examine the behavior of a system under thousands of different conditions in a few minutes, while doing so in practice might take up to years. An additional point of simulation is that it sometimes fabricating the real-world system is impossible, and simulation is the only tool at our disposal. Take weather as an example. We have very limited control over the weather, and all we can and want is to forecast it. By using extensive simulation, it is possible to predict the behavior of the weather to some extent, but there are no alternatives. Now that we have discussed the essentiality of using simulation as a principal tool, it is necessary to move forward and ask ourselves the second question: what is simulation? To give a textbook definition, simulation is the imitation of the operations of real-world processes or systems over time. In simulation, a system or process is chosen, its appropriate model extracted, and its behavior is obtained for a predetermined course of time. Let me provide an example to illustrate this matter. To model the falling of a ball, it is possible to use Newton's law of motion to construct a mathematical model of the ball's movement, and then use that model to simulate the fall under different conditions. In fact, the simulation represents the time evolution of the model with a predetermined accuracy. The next important question concerns the key components of a simulation. To run a simulation, you always need a mathematical model that is constructed to capture the key characteristics of the system of interest and its dynamics. After having your model, which is nearly in all cases include differential equations, you need to solve the model over some time, and for that you need a solver. Based on the mathematics of the model, different solvers are used, and the level of the sophistication of the solver depends on many factors that we will discuss in the next section. The combination of model and the solver makes the running of a simulation possible. Finally, it is important to address one critical question: what are the limitations of simulation? The answer to this question is rather extensive and constitutes of many different aspects, but to note the key concepts, I would say that model accuracy, model simplification, model validity, and the validity of the solver itself are the key limitations. Model validity describes how accurately the model captures the real-world behavior of the system under study, while the validity of the solver is mainly concerned with this question: is the solver that is being used the appropriate one? And the answer varies from field to field and sometimes from case to case. As previously discussed, we will begin to delve into the process of simulation. The first element of every simulation is the model. Please have in mind that several different mathematical models can be used to imitate the behavior of a specific phenomena, and the selection of the appropriate model depends on the aspect that we care about. For example, there are several biological neuron models that aim to describe how neurons fire. The perfect integrated fire model, the leak integrated fire model, the Hodgkin-Huxley model, and so on are just some examples that model this particular phenomenon, and the selection of a model depends on what matters the most to us. Is it the big picture or is it the details? Rationally, as the model becomes more accurate and universal, its level of sophistication also increases and becomes more computationally expensive to simulate. The second element of the simulation is the solver. The solver is the mathematical tool that we use to solve the mathematical model over time. For example, let's consider the falling of a ball subject to air resistance as an example. From Newton's law, we know that the equation of motion can be written as described. Now, in most cases, it is impossible to find the analytical solution to such problems, and consequently, numerical solutions are used. The universality of numerical solutions in treating a wide spectrum of systems makes them a very desirable choice as solvers. Most numerical solutions solve the differential equations by reducing them into first-order ODEs and integrating them over a period of time. Examples of such solvers are Euler's methods, Runge-Kutter's methods, and Adams-Bashford's methods. Please have in mind that the aforementioned solvers are among the strongest and most popular numerical integration solvers in the field of dynamical systems, and would be beneficial to know their structure and functions. Nevertheless, they are coded as built-in functions in both MATLAB and Simulink. In the next video, the idea of numerical integration will be very briefly discussed, but for a detailed explanation, please refer to numerical method textbooks and courses. Stay safe.